Good morning, Cappuccino. May the 4th be with you. It is Monday, April 4th, and pretty simple warm-up for you today. So let's get on it and get the first 5 people who get it correct will get 5 points extra credit. The second term of a geometric sequence is 6, and the fifth term is 162. Find the 10th term. Okay, so key word here, it's a geometric sequence. So look over your notes from geometric sequence and figure it out. Several ways you could go about getting the answer to this one. All right, good luck. So I wanted to tell you about today's assignment. There's not going to be notes. It's going to be another investigation, and then I will go over the warm-up from last Wednesday, the last assignment that I gave you, just last Wednesday. I'll go over that warm-up. So the investigation today is about series. What is a series? Well, a series is when you take a sequence and you add all the terms together. So you are going to be looking at 2 very famous mathematical puzzles, if you will. The first one is a story about Carl Gauss, who is a very famous mathematician and physics guy. And this is supposedly a story about him when he was a kid, so good luck with that. And then I wanted to point out that the last question here asks you to use the formula to find Pablo's lifetime earnings. Who the heck is Pablo? Okay, Pablo was one of the other investigations from last week. So you need to grab the investigation from next week, which was, I don't have it handy. But anyway, it was the arithmetic sequence investigation. Okay, so go find the assignment from last week. I believe it was last Monday. You did this one where it had information about Pablo and Pablo's salary. Okay, so you're going to use the information about Pablo to answer this question. All right, so this one's all pretty straightforward. The next one gets a little tricky, investigation number 3. The first couple of questions are maybe a little hard to understand. They took me a while to kind of figure out what was going on. But they give you a hint because they say the result obtained in part B can also look like this. Okay, so that kind of gives you a hint as to where you're headed. So number 1's not so bad. Number 2A, it took me a little finagling to figure it out, but basically you're trying to get to this result. So try and follow that if you can. But you should, even if you can't quite figure out how to do part 2, okay, number 1 isn't so bad. Number 2 might be a little tricky. If you can't, no worries. You'll still be able to do this problem here, which again is another sort of famous mathematical puzzle about grains of rice on a chessboard. So you should be able to finish this. So don't stop here on problem 1 or 2 because you're confused. Don't stop, just keep going, and you should be able to figure out the last one. Okay, it's not that bad. All right, so that's what you're doing today. Now, to go over from last week, the last warm-up, let's go over these. Most people who turned it in were able to find the volume of revolution around the x-axis, so taking this little green area here and revolving it around the x-axis. Most people were able to do that. The only tricky thing on this was realizing that when you set up your integral that you needed to figure out this x value right here. You needed to know what is the x-intercept. Okay, so a couple ways you could have done that. I said that you could use a calculator, so you could have just put this into the calculator and figured out the x-intercepts. The other way, of course, is to set it equal to 0 and figure out what the x-intercepts are. So I'm going to go ahead and do that. So this can be factored. So I'm going to do what my son calls the Windmill Method. I'm going to x squared is x times x. 6, I can do 2 times 3 or 3 times 2 or 6 times 1 or 1 times 6. But I notice I'm trying to get a 1 right here. So I'm going to do a 3 and a 2. And it needs to be negative. So I'm going to make the 3 negative because I want more negatives than positives. And if I windmill this, x times 2 is 2x. Negative 3 times x is negative 3x. And if I add those together, yes, I get the middle term. So that means that this factors to x minus 3 times x plus 2. And if I solve that, I get x equals 3 and x equals negative 2. So this would have been negative 2. So notice I said not drawn to scale. You had to actually do this work yourself, and 3. Okay, you also could have done that on your graphing calculator. You could have just put it in and found the intercepts. So when I set up my integral, I'm going from 3 to 5. And I'm going to have my pi, I'll put it out here, and then I'm going to have my y squared, so this is going to be x squared minus x minus 6, the quantity squared, dx. Okay, so that was another mistake. People forgot to put the squared. You got to square this quantity. So I did say you should use a calculator. A calculator is advised. You do not need to simplify this. Some people try to distribute this too. You cannot distribute an exponent over subtraction or addition. You would have to write this out twice and distribute, use the distributive property. But there's no need to do that. You can go straight from here, straight to your handy-dandy calculator. So let me, oh, do I have it in there? No, let me clear that out. So I'm going to put in my, oops, I'm going to put in parentheses, x squared minus x minus 6, close parentheses, and then square it. Okay, you can put that whole thing right into your calculator. And then I'll go ahead and graph it. And then I want to find the integral. So option 7 from 3 to 5. And I get 113 approximately. So this is equal to approximately 113, and don't forget the pi. And then that is a volume, so it'd be units cubed. Okay, so that was A. All right, so the tricky part on here again was just figuring out that you needed to go from 3 to 5. You needed to find that x-intercept, and then don't forget to square the function. All right, this one, whole new ball game on this one. If we're revolving around the y-axis, we need to solve this equation for x. But we've got a couple of x's here. We have an x squared and we have a plain old x. So that's what made this really tricky. Okay, another thing is that you needed to make sure you were evaluating it from here up to the top, wherever this intersects with 5. So up to here. So when you're setting up your integral, you're going to be going pi, and you're going to be going from 0 up to, well, what's this value up here? Well, that value up here is where x is 5, what's y? So you can just plug in what happens when x is 5. So I have if x is 5, 5 squared minus 5 minus 6, I get 25 minus 11, which gives me 14. So, or you could have done it on your graphing calculator. Actually, that's not so easy. Now, the easiest way to do it is just to substitute in 5 for the x and figure out what's the value of y when x is 5. Oh, my dog wants in. Hold on a second. Little dog. Okay, back to work. All right, so now for the hard part. I have to rewrite my equation in terms of x. So to do that, I was thinking, well, I need to get an x by itself, but I've got these two different x terms. So how am I going to do that if I can't combine those like terms? And then I realized, oh, I could complete the square. When you have completing the square, you end up with only a single x in the equation. So I'm like, okay, I'm going to take my x squared minus x minus 6, and I'm going to complete the square. So when you complete the square, you take that middle term and you divide it in half, and then you square it, and then you add that to both sides of your equation. Actually, I like doing this first. I like moving my constant, I like moving it to the other side. So actually, let's go ahead and do that first. So let's get rid of that minus 6. I'm going to add it over here. Okay, so I moved my minus 6 to the other side. So now I'm going to take negative 1/2 and I'm going to square it. Negative times a negative is a positive. 1/2 times 1/2 is 1/4. So I'm going to add 1/4 here, and I'm going to have to add 1/4 to the other side as well. Okay, so now this, because I'm completing the square, I know that I just use this guy right here. X minus 1/2 squared is equal to y plus 6 1/4. Okay, and you could test that. You can multiply this out, and you realize, yes, you do in fact get x squared minus 1x plus 1/4. All right, so now, see, I almost have x by itself. What I need to do now is get rid of the square, so I'm going to square root both sides. So square root both sides, and I get x minus 1/2 is equal to the square root. It would be plus or minus the square root, but we don't need to worry about the minus side, because that would be this side of the graph. I only want the positive side. So it's equal to the square root of y plus 6 1/4. I'm going to just change that to a decimal just to make my life a little bit easier, because I'm running out of room. And then I'm going to add 1/2 to both sides. So x is equal to 1/2 plus the square root of y plus 6.25. Okay, so I did have some students get this, solve for x by using the quadratic formula also, and that was very clever. Okay, tricky, but very clever. Okay, so now that's my x, so I'm going to have 1/2 plus square root of y plus 6.25, all of that squared dy. Okay, but that would get me the volume of just taking this curve and revolving it around the y-axis. That would actually get me all of this. But that's not what I want. I want in between here and x equals 5. This line is x equals 5. Oh, what do I do when I want the region in between two curves? I have to subtract them. Okay, so think about it. If I turn this sideways, who's on top? X equals 5 is on top. So I'm going to start actually with x equals 5. That's going to be my first function minus my second function, which is the x equals 1/2 plus square root of y plus 6.25. So this is not going to get me the answer I want. I did have a bunch of people get this and figure out what this equals, but that would be this region in between the curve and the y-axis being revolved around. But I want this region. So you can think about it. If you just took this x equals 5 and revolved it around the x-axis, you'd have a big fat cylinder. And then if you took this area, this region, that would be this kind of cup-shaped region in here. If you revolve that around, it would be kind of like a cup that tapers down at the bottom. Okay, it would be a nice cup. So, but we want the volume of the region between the cup and the cylinder. So what we can do is we can just subtract them. So I would have pi. Okay, to get the volume of the cylinder, it would be this equation squared. So this equation is just 5. So 5 squared minus the volume of this region. So minus 1/2 plus the square root of y plus 6.25 squared dy. Okay, oops, all of it dy. So then if you just plug that into your handy-dandy calculator, we will get the answer. So if I go in here, I'm going to put in 5 squared, or 25. Okay, I'm just going to write 25 because I know 5 squared is 25, minus parentheses 1/2, or we can just do 0.5 at this point, plus parentheses, because I'm going to use an exponent for my square root, y plus 6.25, close parentheses, raised to the 0.5, because square root is a 0.5 is the exponent. And all of that in parentheses, because all of that needs to be squared. And let's graph that, see if I made any mistakes, see if it gives me an error if I typed something in wrong. There it is. And we want to evaluate it from 0 to 14. So I'm going to go second, calculate, number 7. Lower limit is 0, upper limit is 14. Nope. And we get 110 2/3, Or if we're rounding that off, we could say 111. And don't forget the pi from out here. And then again, that's units cubed. All right, so the only person who actually got the correct answer did not do it this way at all. They used a completely different method, and that method is called, oh my gosh, what was it called again? It's called the cylinder shell method. That's it. Cylindrical shell method. And I wrote down the formula for that, and it's actually a lot easier in a situation like this, when you've got some weird shape to rotate around the y-axis. Cylindrical shells is the method. And in this case, we actually don't have a second curve, really. You don't have to worry about that. Cylindrical shells method, it's basically you're taking a very, very thin cylinder, and you're finding a whole bunch of cylinders that you can sort of nest inside of each other, and you're adding them together. So rather than going over it myself right now, I included a link in Canvas to a Khan Academy video that does a really nice job of explaining it, because he can draw way better than I can. It really helps to have the visuals on this one. So those of you who plan on being STEM majors, or actually not so much science, but those of you who are planning on majoring in engineering or physics, I would recommend that you go watch this video. And those of you going on to HL next year, I would recommend that you go watch this video, because this shells method is actually, the math involved is way easier than what I just did right here. It's actually super easy. But I want you to conceptually understand it, okay? So go watch that video on the cylindrical shells method and for another way to do this problem B. And look forward to an extra credit assignment in the future involving the cylindrical shells method. It's way cool. All right, so good luck. No notes today. Instead, this investigation. Okay, this is going to be assignment number 100. And again, if you get stuck here at the beginning of investigation 3, just skip it. It's okay. Just skip it and move on to the back side, okay, and do this famous story. And you could probably even look up the answer if you're having a hard time with it, because this is a really famous mathematical puzzle. All right, good luck, and talk to you tomorrow. We will have office hours as usual on Wednesday and Friday, 10:30 on Wednesday, 10:20 on Friday. Bye-bye.